In this video, we'll continue our discussion of examples of rings. Our next big example is Z mod NZ. This is a commutative ring with identity. The identity is 1. So as long as n is greater than or equal to 2, that you're not taking Z mod Z, we have a non-trivial ring. So how do you multiply residue classes? So let's say the class of A times the class of B is the class of A times B. So I'm going to be a little informal, and often I'll write A for both an element of Z mod NZ and for an integer that is in that residue class. So what are the units here? So the units are the classes A where GCD of A and N equals 1. So it's if A is an integer where GCD AN equals 1, the class of A is a unit. So let's prove this. Let's first suppose that A is an integer where GCD of A and N is 1. So what does that mean? One thing it means is there exist integers x and y such that ax plus ny equals 1. So if we look at this equation, mod n, we get ax plus ny is equivalent to ax mod n, which is equivalent to 1 mod n. So the left-hand side is equivalent to ax, the right-hand side is equivalent to 1 mod n. So what does that mean? There is some other residue class, the class of x, some other element of Z mod NZ, where A times x is 1 in Z mod NZ, is the multiplicative identity. This ring is commutative, so if ax equals 1, xa equals 1 as well, and that means that A is a unit in Z mod NZ. So for this next part, I want to be a little more clear about distinguishing between an integer A and the residue class that you get in Z mod NZ from A. So let me say if A bar is a non-zero element of Z mod NZ, we're just going to choose a representative integer in this class. Let's call it A. So let's suppose that the GCD of A and N is bigger than 1, is D. So that means D is between 1 and N. How do we know that D isn't equal to N? Because if it were, then N would divide A, and the class of A would be 0 in Z mod NZ. All right, so we're going to define the integer B to be N over D. So what does that mean? The class of B is non-zero in Z mod NZ because D divides N. So N doesn't divide B. So N does divide A times B because we have N over D times A, and we know that D divides A. So N divides the integer A times B. So if you take the corresponding residue class, the class of the integer A times B, that's the class of A times the class of B in Z mod NZ, and that is 0. That product of elements of Z mod NZ is 0. We know that the class of B is not 0. So that means A is a 0 divisor. The class of A is a 0 divisor. Okay, so what are we seeing here? We're seeing that every element in Z mod NZ, this finite commutative ring with identity 1 not equal to 0, is either a unit when GCD of A and N is 1. So that is, we pick a residue class in Z mod NZ. We can think of these as being like the integers from 0 to n minus 1. And we just take some integer in that class and compute the GCD of A and N. So you get a unit when that GCD is 1. And if that GCD is bigger than 1, then you get a 0 divisor. So this is one instance of what we proved in the last video, that in a finite ring with identity, every non-zero element is either a unit or a 0 divisor. So I'll pause and erase, and I'll talk about a new type of example of rings that come from functions. Let's consider our next big class of examples, which are rings of functions. We'll start with a totally general setup. Let X be a non-empty set and A be any ring. And let's let R be the collection of all functions from X to A, where if we want this to be a ring, we need to say what are the addition and multiplication operations, and we'll define them pointwise. So what does that mean? F plus G, to define this function, we have to say, what does it do to each element X in our set X? F plus G of X will be F of X plus G of X. And f times g of x will be f of x times g of x. It is straightforward to check that this is a ring. You should do that. Also, it is commutative if and only if A is commutative. And it has an identity if and only if A has an identity. So this ring of functions inherits some structure from the ring A. So this setup is so general that there's not much that we can really say about it. But if you impose additional structure coming from X and A, you can get a lot of interesting examples. So just to start with one, let's say that A is R and X is the interval from 0 to 1. And let's not consider all of the functions from 0, 1 to R, but the ring of all continuous functions, f from the interval 0, 1 to R. So you can check that this actually is a ring. It's an exercise to show that with this pointwise product, that the sum of continuous functions is continuous. It's a little bit more work to see that the product of continuous functions is continuous. All right, so let's consider one function, f of x equals x minus 1/2. So we can ask, like, what do the units in this ring look like? What do the zero divisors in this ring look like? So here's an example to start with. This has a 0 at 1/2, and that's enough to say that it's not a unit. Because if it were a unit, you would need a function g where f times g was equal to the multiplicative identity of this ring, which is the constant function 1. So in particular, g of x times f of x would have to be equal to 1 when x equals 1/2. But since f of 1/2 is 0, no matter what g does at 1/2, the product is going to be 0. So this product can't be the constant function 1. Okay. Well, let's ask what has to be true about g if g times f is the additive identity in this ring, which is the constant function 0. Well, if g times f equals 0, then g of x must be 0 for all the places where f of x is not 0. So g of x is 0 whenever x is not equal to 1/2. But the only continuous function that is 0 on the whole interval from 0 to 1, except maybe it's something else at 1/2, is the constant function 0. That if g is equal to 0 on like an open neighborhood containing 1/2, or an interval containing 1/2, then it's also 0 at 1/2. So the only continuous function with this property is g of x is the constant function 0, which means that that f of x is not a 0 divisor because there's no non-zero function g that we can multiply it by to get 0. So it turns out that this ring does have a lot of 0 divisors. This just isn't one of them. So I'll pause and erase and give some examples of 0 divisors and say a little bit more about rings of functions. Let's continue our discussion of this example. We looked at this one function, f of x equals x minus 1/2, and saw that it was not a unit and not a 0 divisor. But this ring does have many 0 divisors. For example, we can define something that looks like this f from before, but in a piecewise way. So let's say f of x is 0 on the interval between 0 and 1/2, and then is x minus 1/2 between x equals 1/2 and x equals 1. So what does it look like? It's 0 along the first half of the interval, and then it's this linear function after that that peaks at 1/2 at x equals 1. And let's just define g of x to be f of 1 minus x. So what does that mean? You take the interval from 0 to 1 and you kind of like flip it this way. Okay, so g looks like this. Then the product, g times f, is a continuous function from the interval from 0, 1 to r, but it's 0 everywhere. So this f and this g, these are two examples of 0 divisors. Okay, so I'll pause and erase and then give some last examples of rings of functions. I just want to briefly mention two other examples that come from rings of functions. Let's consider the ring of all functions f from R to R with compact support. So what does that mean? For any function f, we want there to be an a and b in R such that f of x is 0 outside of the closed interval between a and b. So every function f can be non-zero at most on some closed interval between a and b. It's a good exercise to show that this actually is a commutative ring. And there's no identity. Why is there no identity? Because the identity that you want to have is the constant function 1. That's 1 everywhere. But that doesn't have compact support. There's no a and b, so that the constant function 1 is 0 outside of the interval from a to b. So let me talk about one final example that sort of builds on what we've seen already, which is the ring of all functions from the interval from 0 to 1 to R. What are the units? The units are all the functions that are not 0 at any point. So we saw in our discussion earlier that when we had a function that vanished at one single point at x equals 1/2, that meant that it couldn't be a unit. So the units are exactly the functions that don't vanish at any point. And this is an interesting case. If f of x is not a unit, then it must be a 0 divisor. So why is that? Well, let's suppose f is some non-zero function, and we just know that it's 0 at least one point, so that it's not a unit. We'll define g of x to be 0 if f of x is not 0, and it'll be 1 if f of x equals 0. So because we know it's 1 at least one point, this function is not 0. But from how we've defined it, the product, f times g, is 0. So we have this product of these two non-zero functions that is 0, which means f is a 0 divisor. So we know that in general, it's just not true that in an infinite ring, every element is either a unit or a 0 divisor, but it is true in this case.